Welcome to Khetz and in this video I will be talking about straight lines and some basic principles of circles, so circle geometry. But before we get into that, I just want to start with a few things which you have to remember. I'm sure you've learned this in previous grades, but these things are quite important. So let's get right into it. Please subscribe if you haven't subscribed, and if anything I say in the video is not clear, if you don't understand something, then please tell me in the comments. So let's start over here. Now here you have a straight line and you have two lines which intersect or meet at the point A, and we're told that adjacent angles on a straight line are supplementary. And what that basically means is that if you add all of the angles along a straight line, you should get 180 degrees. That is the first one. Moving on to the second one, it says angles around a point sum to 360 degrees. So got a similar thing, but we're now dealing with this point over here. And if you look, you have angles around that point, and what this is saying is if you add all of those points or all of those angles which surround the point, you actually get the sum of all those angles as 360 degrees. Moving along to the third one, it says vertically opposite angles are equal. So now here are the vertically opposite angles. I'm just going to highlight them. So O1 is vertically opposite. So vertically opposite just means it faces it. So there's a point and these two face each other and these two face each other. So that is what we mean when we say vertically opposite. So O1 is equals to angle O3. And angle O2 is equals to angle O4. That is what that means. Now moving on to this one, it says corresponding angles are equal. Now if we say that angles are corresponding, you have some sort of F shape which looks something like that, and you have parallel lines, which is what we have in our case. We have parallel lines, so that qualifies. And therefore this angle and that angle are equal. So basically F1 is equals to A1. Moving on to this one, which looks like a Z. So some other people might actually call it Z angles or whatever that the case may be. So it's a Z in a way or something like that. It doesn't really matter the orientation. But the main thing is that the angle here and the angle here are equal, the angle here and the angle there are equal. In this case, we have an angle there and an angle there, and parallel lines. It is important that you have parallel lines. This only works when you have parallel lines. And it says alternate angles are equal, which means F1 is equals to B1. Moving on to this one over here, it says co-interior angles are supplementary. Now, if we talk about co-interior angles, you have two parallel lines. It doesn't matter if the parallel lines were orientated maybe something like this. These two angles would still be supplementary. Doesn't really matter. As long as the angles are found between parallel lines at positions which look something like this, then co-interior angles will be supplementary, which basically means that A1 and B1 add up to 180 degrees. So that is basically all that I wanted to talk about with respect to straight lines, and we're gonna move straight funny. Then we're gonna move right straight into circle geometry, right? So I have quite a few circles drawn up here, and I'm just gonna explain all of the principles or all of the rules that you have to know. And once you know something, then you can basically apply it. And my next video will be about examples. So we can't apply something which we don't know. So let's first focus on learning this stuff, or let's first focus on knowing what the principles or the laws of circles actually say. So starting with this one over here. So this will be our first one. Let's just label it 1, just so we are on the same page. So we're going to start there, and we are actually saying if we're given AC, which is AC, so if we're given AC perpendicular to OB, which is the line drawn from the center to the point B on AC, then we can ultimately make a conclusion, right? And that conclusion would be that AB is equals to BC. And we actually have to associate all of our conclusions with reasons. And the reason for this will be line from center perpendicular to chord. So you have a line from the center which is perpendicular to this chord AC, and therefore from that you can conclude that this line actually bisects the line AC, and therefore you have AB equals to BC. We're now going to move on to a similar case. So let's say you have the same diagram, which is number 2. Let's say you have the same diagram as number 1, and now you're actually told that AB and BC are equal. So what conclusion can you make? It's actually just an inverse of the first one. The conclusion you can make is that your AC is perpendicular to OB. So in the first one, we're given that AC is perpendicular to OB, and we concluded that AB is equal to BC. But now we're given the conclusion of the first one, which is that AB is equal to BC, which means we can conclude that AC is perpendicular to OB. And the reason for that, also have to provide a reason in this case. The reason says line from center to midpoint of chord. Right, and that is the reason associated with that. We're now going to come up here. So let me create some space. I just want to create some space. Where can I create some space? Okay, so we're going to shift the stuff as we go along because it's getting quite crowded. So now we move on to number 3, which is over here. So we're given that number 3, we're given that A to D are on the circle. So the points are found in the circle. As you can see, A, B, C, D are on the circle, and E is included as well. So that should say A to E are on the circle. That's what that should say. So A to E are on the circle. A, B, C, D, E are on the circle. And from that, we can conclude. We also have a point here at the center. Let's just assume that the point O is at the center, and therefore the conclusion that we can actually make from that is, so let me select all of this so I can take it down so we have some space to work with. Okay, cool. So now the conclusion we can make from A, B, C, D, and E being found on the circle and O being the center is that O1 is equals to twice the size of E, and it is also twice the size of D. Also, we're going to say O2 is twice the size of B, right? And the reason for that would be the angle at the center point, or the angle at center, is equals to twice the angle at the circumference. So that is the reason for that. So you have a center O, and you have O1 and O2, and O1 is equals to twice the value of E, and O1 is also equals to twice the value of D, right? And we can move on to another one, which is the one which you just translated down here. So let me just select it again so we have more space. So let's take this one down again. So this is going to be, I think, number 4. Yes, it's going to be number 4. So let's work with this now. We add number 4. And we're given that AB, so AB, which is over there, is equals to DE, which is over there. So it's actually indicated using these lines which show equality. And we can conclude that the angles C and F are equal. And the reason for that will be equal chords subtend equal angles. This is expected, and it's quite similar to the rule which we talked about when we were dealing specifically with triangles. But now the reason for that is equal chords subtend equal angles. So you have ED equals to, or DE equals to AB. And if you check, AB looks at C, or it faces C, and DE faces F. And that is why we say that equal chords subtend equal angles. Moving on to let's say number 5. We're going to take it up a bit as well, just so it has space. So we're going to take it up. Let me just reselect number 5. Okay. Just want to move this if it can move and it's not responding. Okay, fine. Let's just work with it. Try to work. Okay, let me try one more time. We can just basically work with it from like this point where it is right now, because it's not moving. Okay, let's just write here or continue here. So given that AB is over there, it's the diameter. And our conclusion, or the conclusion that we can make, is that C is equals to 90 degrees. And the reason for that would be angle in semicircle. Angle in semicircle. So basically the diameter is a line which moves from one point of the circle to the other point, passing through the center. So this is the center. And now if you draw a diameter, this is half of the circle and this is half of the circle as well. Now if you look at that, this angle actually supports the reason. You have 90 degrees, and the reason for that is angle in semicircle. So the angle is in the semicircle, and if you form a triangle like that from the diameter, you expect the top angle, or the angle which faces the diameter, to be 90 degrees. So that is what that rule is basically saying. And we can move on to this one over here. So this one actually moves. Let me try to reselect it properly. So I'm just gonna select okay, and do that as well, and do that, I'm not quite sure what happened here. Okay, it doesn't really matter. But let's say we have, so I'm just gonna check this there and take this here, then pick out the circle and put it somewhere there. Yeah, that looks a whole lot better. Now here we are actually given the conclusion from the first one, right? So this is so this one here is number 5. So this one will be number 6. This one will be number 6. So let's write number 6. We have a triangle which is formed by the diameter and 2 lines, and we're given that this angle is actually C, right? C is equal to 90 degrees. So given the conclusion from the previous one. So I've already said the answer, or I've already said what we can conclude if you were listening carefully. And the conclusion we can make is that AB, which is that over there, is a diameter. And this is because the 90 degrees is the same as in number 5. And if we are given that this is C is actually 90 degrees, the only way that that can be is if AB is a diameter, and that is why we made that decision or that conclusion. And your reason, if you were to answer questions, you'd say basically chord subtends a 90-degree angle. You can't call it a diameter as yet because you weren't sure in the first place, and that is why we use the term chord. So now we move on to number 7. So let me try again just to shift this, if that will be possible. This is number 7. I'm going to try to take it up. Okay, that should be fine. So this is number 7. We are given that ABCD is a cyclic quadrilateral, and the conclusion that we can make is that A is equals to B, and we can also conclude that D is equal to C, and the reason for that would be angles in same segment. So angles in same segment. That is basically the reason for that. If you have a cyclic quadrilateral which looks something like this, and you are asked to find A and B, or you know A, or you know either A or B, then you should know that A is equals to B and D is equals to C because they are called angles in the same segment. And we're now going to move on to number 8, which occurs right below number 7, and it has basically a similar diagram, but now you notice that there isn't any circle. We're given that A is equals to B and D is equals to C, which is the conclusion that we previously made. And therefore, the conclusion that we can make is the inverse, or it is actually the given statement of the previous one. So you would have noticed that if the conclusion of one diagram now becomes the given statement, then the given statement of that previous diagram becomes the conclusion. So now that we know that A is equals to B and D is equal to C, we can conclude that this diagram is actually a cyclic quadrilateral. So AB, CD, that will be our conclusion, is a cyclic quadrilateral. Just try to quad, doesn't really matter. And the reason for that would be line segment subtends equal angles on the same side. So you'd see that the equal angles are on the same side. A and B are on the same side, D and C are on the same side, and that would be your reason. Moving on to number 9, I believe. So let me try to take this up as well. I should have spaced these when I was drawing them, but I didn't realize that I actually take up a lot of space when I'm writing. So always plan ahead. So that's a tip. Okay, so this is number 9, and we're given that ABCD is a cyclic quadrilateral, and what we can conclude from that is A added to, what is this here that we have at C? A added to C is equals to 180 degrees, and the reason for that would be opposite angles of a cyclic quadrilateral are supplementary. You can just leave it like that, opposite angles of a cyclic quadrilateral, right? Now, if you look at this diagram, which is quite similar to it, it says that we are actually given A plus C equals to 180 degrees. That is our given statement, and this is number 10. A given statement is that A plus C is equals to this plus that is equals to 180 degrees. So what can we conclude from that? So previously, we would saw that it's a cyclic quadrilateral, and we concluded that A plus C is equals to 180. But now that we're given that A plus C is equals to 180, we can conclude that this quadrilateral is actually a cyclic quadrilateral. So cyclic quadrilateral just basically means it's one in a circle, even though the circle is not actually drawn in here. But we can assume that it's actually, or we can conclude that ABC is a cyclic quadrilateral because it satisfies, or it is in keeping with the rule that says opposite angles of a quadrilateral add up to 180 degrees, and that is our reason. The reason would be opposite angles supplementary, so basically add up to 180 degrees. Now moving on to number 11, which is quite crowded as well, but we can try to move it if I can. I don't. Okay, let me try to do that. First I have to erase this, then I'm going to try to remove number 11, which is over here, by selecting all of that. Then I'm going to move it up. Okay, so that's okay. Then erase this point P, it's supposed to be here. Okay, so what can we conclude from this? If we were given ABC is a cyclic quadrilateral, we can actually conclude that A is equal to C1. So this A over here is equal to this C1 over here. And the reason for that would be that exterior angle of a cyclic quad. So expect the exterior angle of a cyclic quad to be equals to the interior opposite angle, and that is just a rule. So if ABCD is a cyclic quadrilateral, we expect C1, which is outside the exterior angle, to be equals to A, which is the opposite and interior angle of the cyclic quadrilateral. So we now move on to a similar one, which is a similar diagram, just that we swap the given and the conclusion. So that is basically all you have to do. You just swap the conclusion and the given statement. So basically here we're given the previous conclusion. So given that A is equals to C1 over there, right? And so that those two are equal. And our conclusion will be that A, B, C, D is a cyclic quadrilateral. And the reason for that would be what we see with our own eyes, which would be that the external angle is equals to the opposite interior angle. So once again, you're basically just swapping those two around, swapping the given as well as the conclusion. So now let's try to remove this diagram as well, and then we're going to solve it, or we're going to look at it in a bit. So I'm going to take it up, and this should be number, so we're at number 10, then we did, this was 11, and then this was 12, which means we're currently at 13. So this would be number 13 that we're working with now. Now that we have 13, we're given that AB and BC are tangents. So AP, that is, so P is over here. We're given that AP and BP are tangents to the circle. So what conclusions can we make from that? So just given that diagram, we can conclude that AP is equal to BP, and the reason for that would be tangents from same point. So if you have tangents to the circle which originate at the same point, let's say P, or P in our case, then you can conclude that those two tangents are equal. Moving on to number 14, I have number 14 over here, right? We're given that AB is a tangent at C, and C is this point over here. What can we conclude from that? We can conclude that OC is perpendicular to AB. So if we have a line which originates at the center and it goes to a tangent, we can conclude that the line from the center is perpendicular to the tangent. And the reason for that would be line line to perpendicular radius, or we can say tangent perpendicular to radius. That is what we can basically say, right? So that is what we have over there, and we can now move on to number 15. Let's move on to number 15, which is what we have over there. This is number 15, and we have E over here. This is E. So given that ABC is a tangent, so ABC, this line over here, we're given that it's a tangent. So what can we conclude from that? We can actually conclude that angle B1 is equals to E. So this angle inside here is equals to that. You're given a tangent. So basically given a tangent, and we're also given this exterior angle B1, and we can conclude that B1 is equals to E. And the reason for that is angle between a tangent and chord. Right? So we have a tangent and we have a chord. So the angle between the tangent and the chord will be equals to that angle over there. And now we're going to have, we can call it a converse. You can call it a converse if you like. We have the same diagram, but now we're given the conclusion of the previous one. And given that B1 is equals to E, so what can we conclude? We can conclude that ABC is a tangent. And our reason would be that angle between line and chord. So here are a few things to note. Whenever you have to prove, or whenever your reason would be that, okay, let's say if your conclusion is that something is, let's say, a cyclic chord or a diameter or a tangent, you'll notice that you don't actually include that term when you're given your reasons. So in this case, we're given that B1 is equals to E, and we concluded that ABC is therefore a tangent. But in our reason, we didn't talk about the tangent. We only said B1 is an angle which is found between a line and a chord, and that line would be referring to our tangent, which we now concluded to be true, right? So that was all that I wanted to talk about. I just wanted to talk about the theorems or the laws which govern circle geometry. And if you know all of these are the base ones. There are quite a few more. I know so. There are quite a few more. But if you know these, you can actually apply them to solve the problems which are in your syllabus. And these are just about almost all, if not all the ones which you should actually know. And if you know all of these laws, or if you know all of these principles, then your analysis of circle geometry would be quite simple. And this forms a huge part of your paper 2, and therefore you should really know this. And so if you missed something in the video, just watch it again. Or if after watching again you still don't understand something, just leave a comment in the comment section. If you like the video, please go ahead and give it a thumbs up. And if you haven't subscribed, please subscribe. And the next video will be about examples, basically how to apply everything I've been talking about in the previous videos under Euclidean geometry. And I will see you guys in the next video.